What's the difference between convergent and Cauchy sequences? Well, as it turns out, there really isn't one. Let's explore why. Let's draw a number line from 0 to 1 and create an example sequence. You'll probably recognize the pattern. This is the sequence 1 over n. We'll start with the definition of convergence. A sequence converges to some value L if for every epsilon greater than 0, there exists a capital N such that for any value of the sequence after the capital Nth value, the distance between that value and L is less than epsilon. In this case, with our sequence of 1 over n, the value that we approach is 0, and we can even calculate what capital N has to be. For this sequence, it is the ceiling of 1 over epsilon. The ceiling function just means round up to the next integer. For example, take epsilon to be 0.01. 1 over epsilon would be 100. Since 100 is whole, that means that capital N is 100. Plotting this point, we are essentially saying that every value of the sequence after n equals 100 will be less than epsilon. You can see why this is true. If n is greater than 100, then 1 over n will be less than 0.01, or less than epsilon. We can do this for any epsilon, meaning this sequence converges to 0. Now that's all fine and dandy. The slightly more obscure or abstract definition to look at is the definition of a Cauchy sequence. A sequence is said to be Cauchy if for every epsilon greater than 0, there exists some capital N such that the distance between two sequence values after the capital Nth value are within epsilon of each other. Basically, instead of all the values being within epsilon of some fixed value L, they are all within that distance of each other. Looking at our example sequence, you should be able to convince yourself that if two values are within epsilon of L, then they are within epsilon of each other. So our sequence 1 over n is Cauchy as well. This is easy to see because every value of our sequence is positive. But what about a more general look? Are all convergent sequences Cauchy? I claim that they are. Let's take a look at the proof as to why that is. Let's let epsilon be greater than 0. We are assuming that our sequence converges to some value, so we'll call it A. Then we know that since epsilon over 2 is also greater than 0, there must exist some capital N such that all values of our sequence after the capital Nth value are within epsilon over 2 of A. Now let n and m be greater than capital N. The distance between the 2 points must be less than or equal to the distance between one point in A and the other point in A. This is by the triangle inequality. Since each of these distances are less than epsilon over 2, we can confidently say that the distance between a sub n and a sub m is less than epsilon. So now we have proven that every convergent sequence is, in fact, Cauchy. Take a look at this example. Here, the red dot is our point A. You should be able to convince yourself that if two values are both less than epsilon over 2 from the point A, then they cannot possibly be more than epsilon away from each other. This is great. We know that every convergent sequence is also Cauchy, but what about the other way around? Let's go step by step through this proof, looking at examples on the way. Our first claim is that if a sequence is Cauchy, then that sequence is bounded. In other words, the sequence doesn't stretch off to infinity. There is some maximum and minimum value. First, let's just write down the definition of being Cauchy. We know that after some certain point, every value is within epsilon of each other. It might seem weird at first, but pick epsilon to be 1. We can say that after the capital Nth term of the sequence, each value is less than 1 away from every other value that also occurs after the nth term. Now fix m in place to be equal to n. Now, a sub n is less than 1 away from a sub capital N. Here's the key part. Now we pick an upper bound. The reason why no value of the sequence can be greater than capital M is as follows. In the first case, the maximum value of the sequence occurs before the capital Nth term. Then, capital M will be that value. In the second case, the maximum value of the sequence occurs on or after the capital Nth term. In this case, we have already established that every single term after the capital Nth term must be less than 1 more than the capital Nth term. So, if m is 1 greater than the nth term, then it must be larger than every term in the sequence. So, m must be greater than or equal to the largest term in the sequence. The same logic applies to the lower bound for the sequence. Just replace the +1 with a -1. Now, every value of the sequence must be between the upper and lower bounds, meaning the sequence is bounded. Take a look here. In fact, you didn't even have to pick epsilon to be 1. For any epsilon, if the values of the sequence after the capital Nth term are within epsilon of each other, pick a value larger than this range, or equal to the largest term of the sequence if it has already occurred, and you have an upper bound. Same thing with the lower bound. Take some time to grapple with this and explain to yourself why it's true. So every Cauchy sequence is bounded. This is good news. That means that it fits within what is called a compact set. While there are semesters worth of material to explain and understand the true depth of compact sets, all you need to know for this proof is that, in the real numbers, compact is equivalent to saying closed and bounded. Now, we're deep in the woods, I know, so bear with me, but the next part that we have to prove is that if a sequence is Cauchy and bounded, then it has an accumulation point, specifically within the compact set that it is contained in. Quick note. In our claim on screen, we don't actually need a sequence to be Cauchy to prove that it has an accumulation point. We only need it to be bounded. However, I am leaving this in so that we remember that we are proving something larger involving Cauchy sequences. As we have already proven, every value of our sequence is contained within the closed and bounded set from our lower bound to our upper bound that we have already defined. In the interest of time, we're going to skip over a crucial step. We will do this, however, because it has already been proven. This step is showing that every bounded sequence in the real numbers has an accumulation point. This is called the Bolzano-Weierstrass theorem. It's crucial to know, and there are plenty of excellent documents and videos online explaining it in great detail, so we won't dive into the nitty-gritty of it, but we can explain why it must be true. For our first case, consider some sequence that has infinitely repeating values. In other words, it only takes on a finite number of values. This could be something like the sequence a sub n, where a sub n equals the sine of n times pi. Then, since we have infinitely repeating points, we can simply pick a subsequence where every value of that subsequence is the same value. Call that value a. Then it should obviously converge to a. The other case is a sequence that does not have infinitely repeating values. In other words, a sequence that takes on an infinite number of values. This is where the Bolzano-Weierstrass theorem really helps. So just picture having infinite values to choose from in a finite range. For your subsequence, pick values that get super close to each other. Infinity can be hard to picture, but in cases like these, it gives you plenty of options. Back to finitely many values, let's take a look at the sequence a sub n, where a sub n equals the sine of n times pi over 4. Take a look at the first few values of the sequence. 0, root 2 over 2, 1, root 2 over 2, 0. Notice a pattern? Maybe it'll help to graph it. You already know the periodic nature of the sine function. Knowing that this sequence will always take on the same values, all that you have to do is pick values that are the same every single time. In this case, it's every fourth value. For example, a sub 0, a sub 4, a sub 8, so on and so forth, all equals 0. There is a subsequence that converges to 0, and therefore 0 is an accumulation point for this sequence. For any infinite sequence that takes on a finite number of values, you'll be able to find an infinite number of points to where you can do this. If that's a bit confusing to you, then try out a couple examples of periodic sequences. The infinite value case is a bit harder to picture, but just think about an infinite number of points in a finite space. Like I previously mentioned, infinity is huge and finite is tiny, so try to convince yourself that you'll be able to pick an infinite number of values all super close together. No matter how close they have to be, you'll be able to find enough values. Alright, we're in the home stretch now. Time to bring it all together and prove that all Cauchy sequences are convergent. Let's let epsilon be greater than 0, and since we are working with Cauchy sequences, we know that we can find a capital N such that you get the point. The values after the capital Nth term get super close together, specifically within epsilon over 2 of each other. However, we now have that there exists some accumulation point for the sequence, call it a, and that means there exist infinitely many a sub k's that are within epsilon over 2 of a. Here's the key step. Pick a k greater than n where that is true. Since there are an infinite number of these a sub k's that exist, we can do that. Finally, we have that the distance between a sub n and a must be less than or equal to the distance between a sub n and a sub k plus the distance between a sub k and a by the triangle inequality. Those two pieces combined are less than epsilon as we previously mentioned, and so we have that for any n greater than capital N, the distance between a sub n and a is less than epsilon. This is the definition of a convergent sequence. Think about it like this. Since some infinite subsequence converges to a, that means there exist infinitely many terms in the original sequence that converge to a as well. This draws the entire sequence to that point. You could also think about it like this. We kind of skipped over the full proof, but we explained that any arbitrary infinite subsequence converges to some value. This means that every infinite subsequence converges to some value, and since a sequence cannot converge to multiple values, all subsequences must converge to the same value, meaning the entire sequence converges to that value. Whether you understood all of that on the first try or not, give yourself a pat on the back. This is one of the harder concepts to understand in real analysis. Sequences are not the most intuitive, and it takes effort to wrap your mind around, but hopefully this video serves as a good reference. In conclusion, we have now proven that every convergent sequence is Cauchy, and every Cauchy sequence is convergent.